Hello, everyone, and thank you for joining us today. My name is Rebecca Green. I'm a co-PI on this project and senior scientist with NREL, the National Renewable Energy Laboratory. And I'm very pleased to present together today with my colleague and teammate, Alicia Mahan from the Pacific Northwest National Laboratory, or PNNL. This is the first of our SEER webinar series. SEER stands for the U.S. Offshore Wind Synthesis of Environmental Effects Research Project. This project is funded by the U.S. Department of Energy Wind Energy Technologies Office, and the research is being performed jointly between two national laboratories, NREL, the National Renewable Energy Laboratory, and PNNL, the Pacific Northwest National Laboratory. Today's webinar will cover two different topics. The first half of the webinar will be on underwater noise effects on marine life from offshore wind development and the risk to marine life from marine debris and floating offshore wind cable systems, which we'll also refer to by shorthand as entanglement. Next slide, please. By way of an overview of today's agenda, we'll first have a short introduction from our DOE program manager. The webinar will then be largely split between the two topics of underwater noise and entanglement. For each of these topics, we will provide a topic overview followed by a panel discussion with external subject matter experts and a Q&A to hear back on any questions you might have on these topics. And finally, we'll close out with some final remarks. So it's my pleasure now to introduce to you and welcome Joy Page to provide an introduction. Joy wonderfully recently became the new Environmental Research Manager for the DOE Wind Energy Technologies Office. Joy previously served as the Director for Renewable Energy and Wildlife for Defenders of Wildlife, and we are very excited to welcome her in her new role with DOE. Joy?
Thank you, Rebecca. Can y'all hear me?
Yes.
Excellent. Well, good morning, everyone. I am so pleased to help kick off the first of SEER's Offshore Wind webinar series. And again, I'd like to take this opportunity to introduce myself to many of you. My name is Joy Page, and again, I oversee DOE's Wind Energy Technologies Office environmental research portfolio, both land-based and offshore. And it's a really exciting portfolio. And while I may be new to DOE, I fortunately am not new to working with these two incredible national labs, their research, the expertise they bring, as well as the stakeholder outreach to tackle some of these key issues with wildlife and offshore wind. And this is really the whole objective of SEER, right? Is to bring stakeholders together from both coasts so we can increase everyone's understanding of the best available science, both domestically and internationally, to understand what technologies, mitigation, and monitoring can be applicable to the US waters, and probably most importantly, understand how we can prioritize new research, align that research, and reduce redundancy. So next slide. And then, sorry, one more. Thank you. So to accomplish this, SEER contemplates a three-pronged approach. So first, we have a series of research briefs, and then this webinar series, and then finally a series of workshops. Next slide. Thanks, Chris. So for the research briefs, oh, sorry, one more, thanks. For the research briefs, PNNL and NREL have painstakingly reduced this information to 7 key topics. And they've worked really hard with their Science and Technology Committee, both to identify what these key topics should be, and also summarize best available science, as well as monitoring, mitigation, and technology. The second component of this webinar series, this being the first one, it really builds off these research briefs and allows stakeholders to get an opportunity to interact with the researchers and ask their questions. And so there's another one in December, and then 2 more next year. And the final component of SEERS is the 2 workshops. And these 2 workshops will bring together experts on both coasts. And that will be an opportunity where we can identify research priorities for the future. And the East Coast workshop will be working directly with the regional wildlife science entity. And so at DOE, I really see the SEER effort as key to advancing deployment, especially if we're going to reach the goal of deploying 30 gigawatts of offshore wind by 2030. We need to be working together and communicating to align our research investments to target key uncertainties and constraints. And I put a lot of value on this communication and stakeholder collaboration. So if you have any questions or concerns in the research briefs, the webinars, or the workshops, please reach out to PNNL, NREL, or myself. I'm always happy to brainstorm and think through new ideas. So again, thank you so much to PNNL and NREL, and again to the Science and Technology Committee. And I'm really looking forward to today's webinar. So thank you, Rebecca.
Thank you, Joy. Yeah, we are very thankful, I should say, again, just reiterating, to our Science and Technology Committee and our external experts who will also be presenting as panelists today. Next slide, please, Chris. So it's my pleasure to now dive into the first topic, the first of 2 topics for today's webinar series on underwater noise effects on marine life associated with offshore wind farms. Once again, my name is Rebecca Green. I'm a senior scientist with NREL and co-PI on this project. I've worked at NREL for several years now. I primarily focus on offshore wind activities, largely in the environmental arena. I previously worked at the US Bureau of Ocean Energy Management for 9 years. My PhD is in biological oceanography from the MIT Woods Hole Oceanographic Institution joint program, and I've worked in the marine sciences for a little over 25 years now. We will also be presenting, after my introduction today, our external experts who are joining us today as panelists, Rebecca Faulkner and Jim Miller, after my overview of our brief. Next slide, please. So today I'll be presenting the state of the knowledge that was developed through our SEER educational research brief, which will be published soon, on underwater sound and noise, including lessons we've learned from the international arena and are applying to the US Atlantic and US Pacific coast to looking forward at offshore wind development. Underwater sound and noise has been a topic for many years in the international community. To be sure, really decades, it's been a topic of research for decades, to be sure that we understand noise effects on sensitive marine life and the implications of offshore development. In terms of definitions, underwater sound can be thought of as being generated by biological sources. So for example, marine mammals and fish, as shown in the figure here. Physical sources, such as environmental contributions from weather and earthquakes, and finally anthropogenic sources from human activities, such as ship noise, seismic surveys, and wind farm development. Unwanted sound sources, such as those from offshore development, including offshore wind farm development, are referred to as noise. Underwater noise is associated at various levels of intensity with the life cycle of an offshore wind farm and may affect marine life in a variety of ways, as we'll look at on the next slides. Next slide, please. Noise can be generated at different levels of intensity throughout the life cycle of an offshore wind farm and can thus have different effects on sensitive marine life that may be in the environment depending on location and region. During the first phase of the offshore wind life cycle, site surveys occur. This can occur over several years, as seen in the figure here. Seafloor mapping technologies are used, which can introduce noise and operate across a range of frequencies, including the use of multi-beam and side scan sonar, as well as sediment coring technologies. The construction phase of offshore wind farm development lasts for a relatively short period, just a couple of years. However, construction activities associated with pile driving can generate intense noise pulses for some foundation types and will be the focus of several of the slides that we'll look at today. The next phase of development can last for many years, even 20 to 30, and that is the operations and maintenance phase of offshore wind farm development, whereby noise transmission can occur from turbine operation itself, with intensity levels depending on the wind speed and the size of the turbine, as well as support vessels that are used throughout the operations and maintenance phase, and really throughout the entire offshore wind life cycle. And finally, we have the decommissioning phase of the offshore wind life cycle, which lasts for just a couple of years. However, noise can be generated from the dismantling of various components of the wind farm. Next slide, please. Noise can be generated, as I said, by a variety of sources and impacts marine animals in different ways. Those potential risks and effects differ in their ability to hear, the ability of marine animals to hear across sound frequencies. And marine life will respond differently to noises from different offshore wind farm activities. In the figure on the right here, you can see in the top part of the panel the different sources that we just described. And in the lower half of the panel, the hearing ranges of different marine life, ranging from lower frequencies to mid frequencies for fish, sea turtles, whales, and at mid to higher frequencies, seals and sea lions, and dolphins and porpoises, again, depending on the region and the type of marine life present. Noise may lead to a range of effects on marine life, including auditory masking, behavioral disturbance, hearing loss, and non-auditory injury. Injury-causing noise levels are likely to occur within relatively close range to pile driving during the construction phase of offshore wind farm development, while levels causing behavioral effects can extend significantly further. Next slide, please. The risk of injury to marine life decreases with distance from pile driving activities, but the exact distances are dependent on the nature of the sound source, the environment where development is occurring, and the range of species present. A very helpful framework for considering possible effects of noise on marine life is that of the zones of auditory impact. Looking at the figure here on the right, we look at first on the left side where the greatest levels of potential risk occur for the zone of injury. And moving towards the right, we move into the zone of impairment as we move away from the sound source, towards the zone of behavioral response, zone of masking, and finally, as we get more and more distant from the source, we move into the zone of audibility and to a region where noise levels fall below ambient background levels or natural background levels. I should say that this diagram shows equal spacing for the zones here. In reality, these different zones are of different sizes depending on the sound source, the environment, and again, species present. Next slide, please. So we've largely focused on risks associated with the construction phase of the offshore wind life cycle. And there is certainly a difference between the different types of foundations and the types of sounds and intensity of sounds that are generated. So we would like to present a distinction between noise associated with fixed bottom foundations versus noise associated with floating foundations. With relevant to the US Pacific and Atlantic coasts, on the US Atlantic coast, we are likely to see a combination of both fixed bottom and floating foundations used for offshore development. Whereas in US Pacific waters, development will most likely occur with floating foundations given the depths of waters off our US Pacific coast. So in terms of noise associated specifically with fixed bottom foundations, the installation of foundations through pile driving, including for monopiles, tripods, and jacket foundations, generate more noise than other installation methods. As we then turn our attention to floating foundations, the consideration for these foundations are the use of mooring lines and mooring line anchors, which can be installed using relatively low noise methods by comparison. So there is a smaller anticipated impact compared to those used for fixed bottom foundations. We also want to give consideration to the other phases of offshore wind development and associated noise, although those intensities are considered to be lower compared to construction, but certainly more measurements need to be made and more research performed to ensure that this is indeed the case. Seafloor mapping technologies used for offshore wind surveys operate at lower intensities than those used in the oil and gas industry through seismic surveying, but may still cause behavioral impacts on some marine species. Vessel noise can mask communication in marine mammals and certain fish species and may induce physiological stress and impair foraging in fish and invertebrates. And again, vessels can be used throughout the entire offshore wind life cycle. During the operations and maintenance phase, operating turbines can produce nearly continuous but relatively low amplitude sound that may have some behavioral impacts to nearby marine species, though some species may adapt around operational turbines. And finally, there's relatively less literature on decommissioning activities. However, we believe these activities may cause masking, displacement, physiological stress, and other impacts, especially if marine life have aggregated around the foundations, including, for example, associated with artificial reef effects. Next slide, please. Given the many years and decades of international focus on underwater noise and sound, a suite of monitoring and mitigation methods and technologies have been developed to help minimize underwater noise, including associated with offshore wind energy development. Several monitoring methods exist. Underwater acoustic monitoring has been going on for many years using hydrophones. Passive acoustic monitoring in particular has been useful in understanding the distributions and presence of marine life in offshore wind development areas and understanding the potential effects of sound sources and sound noise that's generated. Other monitoring methods that are useful include the use of animal tagging, vessel-based surveys, as well as aerial-based surveys to understand where marine life is located and how they're potentially responding to sound sources, including the use of these monitoring methods for providing baseline measurements in a region. There are also a suite of mitigation methods that are used and required in some cases. Noise reduction technologies have proven effective in European waters and also in US waters with initial developments in the US. Noise reduction or quieting technologies that have been used include bubble curtains, isolation casings, coffer dams, and hydrosound dampeners. As well, time of year restrictions are often used, such as for the North Atlantic right whale and US Atlantic waters, depending on the presence of protected species during certain times of the year, including during migration. Protected species observers are required in US waters to maintain exclusion areas for protected species and ensure that construction activities are not occurring when protected species are in an area. If those species are observed, shutdown and delay of pile driving is required. As well, a soft start for pile driving is another example of a mitigation method that involves ramp up of the sound source. Next slide. As offshore wind development continues to increase around the world and we collect more data, knowledge gaps and research needs continue to evolve. There are a couple of common research needs that we include that require further understanding. For example, cumulative impacts are an area of international focus. And this includes cumulative impacts from offshore wind farms and other pressures at both the individual and population levels for sensitive and protected species. Of importance are also impacts from the future larger scale offshore wind turbines that will likely be used in the United States and US waters, including association with the unique species in these waters, habitats, and the larger turbines. Some key questions for species of concern include, could animals be displaced from the area by noise associated with offshore wind development? Could animal behavior and/or physiological parameters change in response to noise? Could noise disrupt fish and prey species availability? And how do we improve noise mitigation and monitoring moving forward to reduce potential impacts? Next slide. Knowledge gaps and research needs can also be considered for specific marine life groups. For marine mammals, perhaps the most is currently known. However, more information is needed to understand how noise impacts accumulate over time and multiple exposures, how multiple acoustic and non-acoustic stressors interact, and how effects on individuals affect a population as a whole. Fish and invertebrates are also an important consideration. Further research on fish and invertebrates is needed for their hearing thresholds to better understand potential impacts of particle motion, or the back and forth motion of particles, sound pressure, and substrate vibration. Perhaps the least is known about hearing in sea turtles, so we need to better understand turtle hearing to inform predictions of both physical and behavioral effects of noise. Next slide. That concludes the overview of our educational research brief, which will be published soon. And it's now my pleasure and our pleasure to move into the panel discussion for underwater noise. I would like to introduce to you our two external experts who have reviewed our educational research brief and agreed to join us today to help answer questions. Rebecca Faulkner has been based at CFAS, the Center for Environment, Fisheries, and Aquaculture Science for the past 12 years and specializes in the effects of underwater noise on aquatic species. As part of her role, Rebecca provides scientific advice to regulators in England and Wales on the effects of underwater noise from human activities, including for offshore wind farm developments and other large construction projects. Dr. James Miller is a professor of ocean engineering and oceanography at the University of Rhode Island. He has been doing research and teaching in underwater acoustics for more than 30 years now. He has a doctorate from the MIT Woods Hole Oceanographic Institution Joint Program, an MS from Stanford, and a BS from WPI. So welcome, Rebecca and Jim. We appreciate your joining us today. Can you hear me?
Yes, thanks for having us.
Thank you for having me.
Super. Hello, Jim. Hello, Rebecca.
Hi.
We really appreciate your time and joining us from the various time zones, all the way from our US Pacific region to the UK, where you are today, Rebecca. So we have a couple of questions that we prepared and would love to get your feedback on. The first question today that we'd like to hear your thoughts on is, what lessons learned or current understanding would you like to highlight based on your experience for risks associated with offshore wind development and underwater noise? And we'll go ahead and start with you, Rebecca, if you don't mind.
Yeah, of course. I think there's 2 points that I would like to highlight. So firstly, I think it's important that the original environmental impact assessment contains necessary information so that comparisons can be made more easily between predicted data and the actual measured data. So it's important to test the validity of the predictions made and the impact assessments through construction noise monitoring. And acquiring this data can improve models and also show whether the noise models are conservative or not. And then the second point I'd make is if it is assumed that animals respond to sound, so for example, they flee from the source, then those assumptions can have a big effect on whether auditory injury, such as permanent threshold shift or temporary threshold shift, are predicted. So the parameters used in the noise modelling, such as animal fleeing speed, are very important, and these need to be conservative and based on appropriate evidence.
Fantastic. Thank you for those insights, Rebecca. And we'll loop back to some of those topics in a minute. Jim, what are your thoughts on lessons learned associated with risk from noise?
We're following our European colleagues. They've installed many more wind turbines than we have right now in the United States. And we read their papers, we understand what they're trying to tell us. The construction noise that we've measured has been just about what has been measured in Europe. So that's not a surprise. The new technology, however, for operational noise has made I was surprised how low the levels that are coming from the operation of wind turbines. And that was a surprise. It's very, very low level. And in fact, it's much lower than a ship. So that's the two things that I'd like to say.
Fantastic. Thank you for those insights related to environmental impact assessments, parameters used in noise models, and also how much we've learned from our European colleagues so far. The second question that we would love to get your feedback on is what emerging or state-of-the-art monitoring and minimization techniques for underwater noise should be considered for offshore wind development, specifically on the U.S. Atlantic and Pacific coasts. And Rebecca, we'll go ahead and start with you again, please, if you don't mind.
Yeah, sure. So you did mention quite a few in your slides already. So there are long-established noise abatement technologies and techniques which reduce noise at source, so such as big bubble curtains. So bubble curtains are routinely being deployed in some European countries, such as Germany, for pile driving operations. And there is evidence to show that these are effective at reducing the area over which harbor pole buoys, which is a high frequency citation, are displaced. But the application of bubble curtains does depend on having appropriate environmental conditions, such as the right current speed, wave height, and water depth. So there are a number of other noise abatement systems that have been developed and have been successfully applied, such as a noise mitigation screen, which is a big steel shell with a pile sits inside it, and also a hydrosound damper, which is a net with a special sound mitigating element that is installed around the whole pile. And I would highlight that Dr. Michael Bellman gave a very good overview of the various noise abatement systems for pile driving at a recent DOSITS webinar. So I can recommend watching this if anyone would like to know more information. And just to note that in UK waters at present, noise abatement is not being used for pile driving of offshore wind farms. So our mitigation measures largely consist of soft start or ramp up procedures, and where the hammer energy is gradually increased over time, and the use of acoustic deterrent devices to scare marine mammals from the source, and also piling restrictions as well, but largely to protect sensitive fish species such as spawning herring. But bubble curtains are being deployed for the clearance of unexploded ordnance, UXOs, which are bombs on the seabed. So UXO requires a separate marine license as well as an EPS license, a European Protected Species license. So the developer needs to give careful consideration as to how they're going to mitigate the risk of impact on marine mammals.
Excellent. Thank you for those perspectives, Rebecca. And Jim, what are your thoughts on mitigation methods?
Sure. I participate in the rodeo program that's sponsored by BOEM and Dr. Mary Boatman. And we've in Virginia, the two turbines that were installed recently, one had a bubble curtain, one did not. It was Mary's idea. It was a great idea. And we were able to measure the the real impact of the bubble curtain, and it significantly reduced the levels from the pile driving, frequency dependent, but roughly 10 dB, 10 decibels. I'd also like to thank Rebecca for mentioning docets. Docets.org is a great resource. So if you are interested in, decibels underwater versus air and things like that, and all sorts of things underwater, it's a great service. So we're also, in terms of, I'd like to agree with everything about the slides you talked about and what Rebecca's statement, the soft start and the time of year, the new technologies that are coming online for passive acoustic monitoring of marine mammals is very exciting, and we're involved with that also. So being able to track all the whales and where they are, and it's very expensive to stop for these wind farm developers. Once they start, it's difficult technologically and dangerous. So having situational awareness of where these whales are is greatly helpful to the people who are doing the construction. So yeah, the passive acoustic monitoring is very, very important, along with the aerial and shipboard, things like that.
Excellent. Thank you, Jim and Rebecca. And I will also go a second or third that docents.org is a great resource, and we did rely on it as we developed the educational research brief for our SEER activities. So thank you for highlighting that, and also very exciting to see some of these new passive acoustic monitoring technologies that Jim briefly referred to coming online. The next question that we would like to get your feedback on relates to cumulative effects, which we have seen throughout the international community, continues to be of interest and potential concern. Where do you think the most likely cumulative effects will be with other activities, and what are the associated challenges with cumulative impacts analysis? Rebecca, if you don't mind starting us off again, that would be great.
Yeah, sure. So in terms of challenges, cumulative effects assessments are very complex. There's no easy way to undertake such an assessment. In UK waters, the activities of most concern in terms of other noisy activities are likely to be seismic surveys and the clearance or detonation of unexploded ordnance. We have a lot of UXOs in the North Sea. And it's worth noting that activities are not always regulated by the same body. So, for example, in English waters, offshore wind farms are regulated by the Marine Management Organisation, whereas seismic surveys are regulated by BASE, the Department for Business, Energy and Industrial Strategy. So it's a question of how do you bring all of them together under the one process. So in the UK, we have the UK Marine Strategy, and there's also the European Marine Strategy Framework Directive. So one of the objectives of this is to ensure that cumulative levels of noise pollution are managed at a strategic level. So there is that oversight of the different sectors. And it's also worth noting as well that in the UK, for offshore wind farms and other for marine construction projects, each developer is expected to do their own cumulative effects assessment. And this is often based on data obtained from individual impact assessments. So this really highlights the need for consistency and standardization in the methods and metrics used in individual assessments, but also in the overall quality of the assessments as well. And as advisors to regulators, we argue that such assessments will be better led by government agencies on a regional and strategic level, and also by someone who has a clear understanding and overview of all the activities that are going on in the marine environment.
Excellent. Thank you, Rebecca, for describing some of those challenges and thoughts. Jim?
Cumulative effects is sort of the holy grail of our field, because it's so difficult. There's great controversy both on the physics of how you even accumulate sound over weeks or months or years, and then of course on the biological side, on the marine mammal side, or turtles or fish, there's great discussions among biologists about how that's, but it's not all hopeless, because we do have a lot of experience with human impact, cumulative effects on humans. So, there's OSHA regulations for humans working in loud factories with, machines, and if you, are over a certain air dB level for 30 years, you're going to lose your hearing. So there is some hope that we can start to get at that. Behaviorally is, and I'm not a biologist. I have friends who tell me about this, and it's behavioral effects are so difficult to measure and things like that. So you might get an idea if you do a survey before a construction and survey, after or years after. You might, if you see differences, then you'll know something's going on because the whales have left the area or the fish have left the area. But we haven't, usually the fish come because of the artificial reefs and things like that. But so.
Excellent. Thank you for your thoughts on those couple of questions. And I see that we've gotten several questions from audience members. So for the next 10 minutes or so now, we'll turn to some of those questions, which I think build really well on some of the discussion that we've already had together. The first question that we have from an audience member. Thank you for those who are contributing questions through our chat feature. We are actively monitoring that and compiling questions for our panelists today. So one of the first questions we have here is that as oceans get more and more noisy, what sound inputs should we consider as part of baseline levels of noise? So I think this question is really getting at, what do we define as baselines, especially for noise? What are those inputs that we need to include as part of the underwater sound baseline? And I guess Jim or Rebecca, either of you who might have some thoughts on baseline considerations and what to include.
If I could just, let me try. There are people who have, systems, hydrophones out there measuring long-term ambient noise and we have data over decades. And we do see an increase in ocean ambient noise, mainly due to shipping. There was some interesting work in 9/11 with the shipping shutting down and ocean significantly got quieter. There's 2 papers here at the Acoustical Society of America meeting this week in Seattle on if COVID affected it. And if it was detected, it was very, very, very little effect from the shipping decreases and things like that. So that there is a lot of measurements and a lot of people concerned with these long-term noise effects. It's mainly due to anthropogenic sources, of course, due to shipping. So the construction operation of these wind farms will contribute to that. And the question is how much and things like that. I was pleased to see in our own measurements the operational noise from the Block Island wind farm, the first offshore wind farm in the United States in Rhode Island, Little Rhodey, was very low. Much less than a vessel. So that was helpful.
A great observation there, and thanks, Jim, for joining us from the Acoustical Society of America conference today, where you're probably hearing all kinds of great findings hot off the press. So, and thank you for sharing those. Rebecca, do you have any thoughts on this baselines considerations question and the various types of sound inputs that need to be considered?
Yeah, I mean, in the past, developers during the construction noise monitoring, they've gone out and they've taken measurements, so before power driving and then during power driving, so you can clearly see the difference. So that might be something, to kind of consider. I know we've also had discussions whether vessel noise from fishing should be considered as a baseline or not. And some people argue, it shouldn't be, it should be additional. And then developers are saying that it should be included in the baseline. So yeah, there's kind of arguments 2 and 4 really.
Great, thank you. All right, well, we have several more questions in the chat here. So we'll go ahead and walk through some of these. Here's a question. What construction noise mitigations have been used or are planned for use in the US? And what options are being discussed to deal with this issue for larger turbines at new wind farms? I know, Jim, you briefly discussed some of your experience with the use of bubble curtains. So anything else you can say about construction noise mitigation options that you may have experience with or that are planned either in Europe, Rebecca, in your case, or in the US? We'd welcome any further thoughts you have on that.
There is other technologies basically that are incorporated into the pile driving system. It's having bubbles from a bubble curtain, which are from the pipes that are perforated on the seafloor. The bubbles rise up, and that's what we were discussing earlier. There's also a technology where you basically put a lot of little plastic upside down cups underneath this, and it holds the air and it suppresses the noise. And that's a very interesting technology that has been successfully used in Europe. Haven't been used here in the United States, but I'm very interested in that. Maybe I'll let Rebecca jump in and continue.
Yeah, I think the bubble curtain, the big bubble curtain, is the tried and tested method, which is known to work, certainly, and reduce the noise levels. And then, yeah, I think it was the noise mitigation screen and the hydrosound damper, probably the other two as well, that again, I think have been tried and tested and have proven to be effective.
Great. Yeah, thank you for those thoughts as we look ahead at offshore development in US waters. And we only have about 3 minutes or so left. So I think we'll just ask one final question here to maybe sew up and wind up our conversation together today. In our educational research briefs, we've compiled and presented some existing research needs to help us move forward as a community. Based on what we currently know, are there any additional research needs that could be addressed in the near term for underwater noise associated with offshore wind farm development? Yeah. Rebecca, maybe we'll go ahead and start with you again, please.
Yeah, I agree with the knowledge gaps and research needs that you've highlighted in the presentation, and I think the main ones have been identified. I expect we'll start to see some more work coming out on particle motion and substrate vibration in order to try and address some of the knowledge gaps in relation to fish and marine invertebrates. We don't currently have any noise exposure criteria for marine invertebrates, and the current noise criteria we have for fish are based solely on sound pressure. I think better characterization of noise sources is required so that impacts can be fully assessed. And going back to a previous question, we need to better understand the effects of cumulative effects, which is important as demand for our seas and oceans get busier. It's also thinking about the impacts of multiple stresses in addition to noise, such as chemical pollution and fishing. And I think finally, we need to get a better understanding of the effects of noise on critical life stages, so in terms of eggs and larvae, but also the effects of noise on key spawning and migration periods, for example.
Excellent. Thank you, Rebecca. Hopefully these thoughts will help to guide us moving forward. Jim, any thoughts on additional research needs?
I completely agree with Rebecca's comments about the seafloor, the substrate. Our knowledge of how sound propagates in the seafloor is not bad. But the different modes of way the energy from the pile driving construction emanates and propagates through, in the P waves and the S waves and the interface waves, sometimes called ground roll. That's very interesting and something we've been looking at. So I would say and also just the propagation. These oceans, they're complicated. There's a lot of fronts and eddies and the seafloor is not a simple medium, and there's layering and glacial effects and things like that, and it's difficult to model. So more modeling always is helpful with good physics, and then verified with more measurements. And so, because it's just measurements are hard, they're expensive, and yeah, that's it.
Excellent. Well, thank you so much for your input today. We are noting down your thoughts, and again, we'll be synthesizing these as a community related to future research steps and recommendations. So Jim and Rebecca, thank you for both participating in this panel as well as informing our educational research brief. And I hope you enjoy the rest of your conference, Jim. And Rebecca, thank you for joining us late in your day from the UK.
Thank you very much.
It's been a pleasure having you both. Thank you, and working with you. So now we will turn our attention as part of this webinar to our next topic of consideration. And I will go ahead and turn the reins over to my colleague, Alicia Mahan from PNNL. Thank you, Alicia.
Great, thanks, Rebecca. Thanks, Chris. My name is Alicia Mahan with PNNL, and I'll be leading the second half of this webinar on the risk to marine life from marine debris and floating offshore wind cable systems. A little about me. I earned a PhD in ocean engineering from Stevens Institute of Technology. I've been with PNNL for about 8 years. I am a team leader of PNNL's offshore wind and ocean dynamics team. And in addition to managing and supporting the SEER project, I also serve as the program manager for the Department of Energy LIDAR buoy program, where I oversee the deployment of ocean buoys, to support offshore wind. And so today I am joined by two experts in the field of entanglement, Ms. Lauren Sayes with the National Oceanic and Atmospheric Administration, or NOAA, and Dr. Desiree Reeb with the Bureau of Ocean Energy Management, or BOEM, and I will introduce them more formally before the panel discussion. So with that, let's dive in. Next slide, please, Chris. Perfect, thank you. So to get us started, let's talk about floating offshore wind development in the US. So in order to meet our deployment goal of 30 gigawatts of offshore wind by 2030 that Joy mentioned previously, that requires offshore wind development on major US coastlines within the areas that are highlighted on this most recent infographic by BOEM. Floating offshore wind is being planned on the Atlantic and Pacific coasts in water depths ranging from 60 to about 1,300 meters of water, as in the Gulf of Maine on the Atlantic coast and off the Pacific coasts. And unlike fixed bottom offshore wind turbines, floating turbines use mooring lines and inter-array cables that will be floating in the water column, and these cables and lines may present physical hazards to marine life. Next slide, please. Great, thank you. So floating substructures come in a variety of different types that use different types of mooring systems. So this graphic shows several common floating offshore wind platforms. So from left to right, we have a single point anchor reservoir, or spar substructure, a semi-submersible in the middle, and then a tension leg platform on the right. And each substructure, as you can see, is anchored to the seafloor using mooring lines. Catenary mooring lines drape through the water column and are anchored to the seafloor, typically at 3 points at a radius around the turbine. Tensioned mooring lines, as in the tension leg platform, they connect directly to the seafloor using more taut or rigid mooring cables. And then lastly, electrical cables may also be floating in the water column, and these floating cables are also called dynamic cables because their position in the water can move with the ocean current. Inter-array cables are used to connect a string of individual turbines to an offshore collector station. and inter-array cables can be floating or they can be buried in the seafloor. However, in deeper waters, it's more economical to actually use dynamic cables instead of laying or burying them in the seafloor. So next slide, please. Great, thank you. So generally, when we talk about entanglement related to offshore wind, there are two very different types of entanglement that we need to talk about. So first, there's primary entanglement, which is the occurrence of marine life directly becoming entangled with a mooring line or an inter-array cable. Then there's also secondary entanglement, which is the occurrence of marine life becoming entangled with marine debris, including derelict fishing gear that is snagged on a mooring line or an inter-array cable. And when we talk about entanglement risk, we really need to consider these two types of entanglement separately. Next slide, please. Great, thank you. So current literature suggests that the risk of primary entanglement, which is again the occurrence of marine life becoming directly entangled with a mooring line or cable, that risk is actually low because floating offshore wind cable systems are engineered in such a manner to prevent those cables and lines from actually looping and entangling marine life. Floating offshore wind cable systems also occupy a very small cross section of the water column, as you can see in this figure on the slide, and the relative spatial scales of floating offshore wind infrastructure and marine life really further reduce the likelihood of marine life encountering such systems. Incidents of primary entanglement with floating offshore wind cable systems that are associated with oil and gas platforms have not been publicly reported. And those cable systems associated with oil and gas platforms, they're very similar to the floating offshore wind cable systems. So that really suggests that the likelihood of marine life becoming directly entangled with floating offshore wind systems is low. Entanglement reports indicate that fishing gear is the primary cause of concern of entanglement in large whale species. And so therefore the potential for secondary entanglement of marine life with marine debris that's snagged on floating offshore wind cable systems is the leading cause of concern. Next slide, please. Great, thank you. So the knowledge of the potential consequences of secondary entanglement of marine life in floating offshore wind cable systems remains limited because of the infancy of the industry and the lack of entanglement and marine debris monitoring for existing floating offshore wind developments around the entire world. Large migratory whale species, including humpback and fin whales, they are anticipated to be the most at risk of physically interacting with marine debris caught on floating offshore wind cable systems because of their size and their feeding behaviors. And fish species such as whale sharks, basking sharks, and manta rays may also be at risk, as well as sea turtles, seals, and diving seabirds. Next slide, please. Great, thank you. So although the likelihood of secondary entanglement remains unknown, the impacts of marine life entanglement with actively fished and derelict fishing gear may provide the greatest insights into potential consequences with floating offshore wind cable systems. And so, for example, the potential consequences of marine life becoming entangled in fishing gear include, for example, asphyxiation or respiratory distress because of a lack of oxygen, which is known as underwater entrapment, tissue damage, potentially resulting in scarring, muscle and or nerve injury, infection, and in severe cases, death, reduced foraging ability, potentially leading to emaciation, impacts on mobility, including the ability to dive, to migrate and reproduce, and then ultimately impacts on population growth as a result of mortality or reduced reproductive stress for species that have low reproductive rates. And as multiple floating offshore wind arrays are constructed and the number of floating cable systems in the water column increases, the potential cumulative effects of offshore wind combined with other activities will need to be examined. However, it is difficult to determine the cumulative effects of offshore wind due to a lack of projects that are currently deployed, as we previously talked about, and the combined effects of multiple environmental stressors, for example, the presence of these floating offshore wind cables, vessel traffic, underwater noise, may result in biologically significant population level responses in marine life and will need to be considered. Next slide, please. Great, thank you. So monitoring requirements for floating offshore wind cable systems are fairly similar to those that are implied for analogous structures. So for example, floating offshore wind cable systems will require routine inspections during the operation and maintenance phase, which will be typically conducted by remotely operated vehicles. However, these inspections are generally used to confirm the structural integrity of the cable systems rather than conduct environmental monitoring for entanglement. Offshore wind stakeholders have identified the need for routine monitoring and mitigation measures to reduce the risk of entanglement. And some recommended entanglement monitoring and mitigation techniques include the use of underwater cameras, monitoring mooring and line loads or motion, and the use of underwater vehicles to detect and remove marine debris. And for example, the Kincardine floating offshore wind farm in Scotland, they've actually integrated load cells with the mooring lines to periodically monitor mooring line performance and potentially detect the entanglement of floating marine debris, including derelict fishing gear. And this farm will use remotely operated vehicles and vessel-mounted sensors to periodically survey floating cable systems that could also monitor for the presence of derelict fishing gear. Established methods for environmental monitoring can also be used to gather information about marine behavior, their movement, their use of space in the vicinity of floating platforms, which in turn can be used to evaluate entanglement risk and develop mitigation methods. And some of those potential monitoring approaches include aerial and drone surveys, remote sensing technologies such as infrared sensors and radar, passive acoustics, which we've previously talked about, underwater cameras, and animal tagging. Next slide, please. So research is needed to develop more effective technologies for monitoring, detecting, and removing marine debris that's snagged on floating offshore wind cable systems. A quantification of recreational fishing activity in offshore wind areas is also needed to inform estimates of the amount of fishing gear that could become entangled in floating offshore wind cable systems, and also the likelihood of secondary entanglement. And NOAA, supported by BOEM, is actually developing a modeling tool right now to evaluate the risk of protected whale species and leatherback sea turtles in deep water becoming entangled in derelict fishing gear snagged on floating offshore wind cable systems. And this tool will assess whale and sea turtle entanglement risk and the potential severity of entanglement, which will allow NOAA and BOEM to identify mitigation measures that can be implemented to reduce the potential risks of such entanglement. Research is also needed on the habitat preferences, the migration patterns, and diving behaviors of marine life to support a more comprehensive evaluation of entanglement risk, with a specific focus on large whales, large pelagic sharks and rays, and sea turtles. And local scale information about species behavior, their movement, and use of space around floating offshore wind platforms is critical to that effort. And stakeholders really acknowledge the high level of biodiversity present in US waters and the presence of key migration routes for marine mammals, turtles, and birds. And in California specifically, stakeholders have identified the need for additional data about California marine ecosystems and species migration routes to inform the development of approaches to mitigate the risk of secondary entanglement. Federal agencies, many of whom are on this call, are conducting research to assess the abundance, occurrence, and distribution of threatened and endangered species and their ecosystems in areas of the Pacific. And as a nation, as our offshore wind industry grows and planning for floating offshore wind continues, the potential entanglement hazards to marine life from floating offshore wind cable systems will continue to be a high priority for stakeholders. There are several national and international efforts and assessment efforts that are underway to establish a more comprehensive understanding of entanglement risk and develop effective approaches to monitoring and mitigating this risk for offshore renewable energy applications. And really an open dialogue among researchers, the industry and regulators, and the international offshore wind community is needed to share our lessons learned, identify knowledge gaps, and develop research agendas to address outstanding research needs. Next slide, please. Great, well, thank you. And with that, I'd like to thank you for your attention as we talked through the state of the science as it relates to secondary entanglement and floating offshore wind. And if you're interested in learning more, I encourage you to visit the link to TEFIS at the bottom of the slide to access all of the literature that was used to inform the development of this research brief. And next, I'd like to kick off a discussion with our expert panelists, Ms. Lauren Sayes with NOAA and Dr. Desiree Reeb with BOEM. So Lauren Sayes has been working to reduce whale entanglements off the US West Coast for over 13 years. She is a contractor with Ocean Associates Incorporated, working for the National Marine Fisheries Service West Coast Regional Office Protected Resources Division. Lauren is the lead author on multiple NOAA technical memos related to whale entanglements off the US West Coast and is a member of the California Dungeness Crab Fishing Gear Working Group. She received a Master of Environmental Science and Management from the UCSB Bren School of Environmental Science and Management. So thank you for being with us, Lauren. And Dr. Desiree Reeb is a marine mammal biologist with extensive field research. She began working at BOEM in 2013 at the Office of Renewable Energy Programs and transferred to BOEM's Pacific Regional Office in late 2018. Dr. Reeb's main duties involve assessing and mitigating the potential impacts of proposed activities on the outer continental shelf related to renewable energy, traditional energy, and marine mineral development. And in her position at BOEM, she participates in directing BOEM-funded independent marine mammal and sea turtle research to address identified data gaps and inform these environmental assessments. So I can't wait to hear more about that. Thank you both for being here. Wonderful. All right, so let's see. Desiree, if you don't mind. Perfect, great, thank you. So to start off our conversation, I have a couple of questions to start, but I do encourage everyone in the audience to put your questions in the chat that we are actively monitoring. So I have a couple questions and we can kind of flip-flop back and forth with who we can start with and choose who's going to be in the hot seat first. So to kick us off, what lessons learned or current understanding would you like to highlight from your experience for risks associated with offshore wind and entanglement? And Desiree, if it's okay, I'd like to start with you.
Sure. Good morning, Alicia, and everybody who's on the call. Thanks for being here. Can you hear me?
Yes, we can.
Okay, great, super. Thanks for the question. I think, you know, you've covered a lot of things this morning already, but, you know, as you mentioned just a few minutes ago, floating wind is still very new, and we really don't have any commercial scale projects to derive much data from, and the available research is rather limited. Additionally, with current efforts, there's always sort of geographical nuances that are different. For example, in the areas that are currently accommodating pilot projects, they are in generally shallower waters compared to what we have in the US West Coast, and the species diversity is quite different. So I think these are really important things to keep in mind when you start thinking about how to assess these risks. I think one of the things I'd like to highlight is that, you know, you mentioned the study that BOEM and NOAA are partnering on, and what I want to sort of emphasize about that is that we know that marine species become entangled in fishing gear and vertical lines. But the thing we don't really know a lot about is the events that lead up to that entanglement event. So we've been working really hard to try to get a better understanding of the way the various species behave and interact with the gear, because that information will inform risk assessment and also, of course, potential mitigation strategies. So the simulator is incorporating accurate math, physics, morphological information, behavior as best as we have it. And we're hoping that that will try to unravel this sort of element that is really rather unknown and ultimately prevent these potential entanglement events.
Great, thank you. Lauren, do you have anything to add about that?
Yeah, so I'm happy to be here. Thank you for inviting me, and happy to be next to Desiree. You're just a wealth of knowledge. I'm excited to be sharing the screen with you. Yeah, I guess my additional thought after Desiree was speaking was that we don't have a lot of actual comparison. So my background is really just trying to understand what the whales historically have been entangled with, and so there's still a huge part that is unknown. But what we do know is commercial fishing gear, and I guess my continued concern would be, and it was brought up in the chat, is that entangled whales that are entangled with fishing gear have also gotten the gear that is trailing them entangled on other things too. So I think you guys would consider that a tertiary entanglement, because we've had whales that had a trap hanging down and then caught onto a weather buoy or something along those lines. So that's also a concern for me. But yeah, I would be interested to learn more about the lines that are being used. And I do believe that these heavier lines under tension, there's probably much less chance for a whale to get entangled. But my other little note I made for myself was we've had one line out in the middle of this wide open area, and the whales are attracted to it. So very much like what Desiree was saying, is understanding what how these whales, why they would get entangled. So the behavioral part of it is very interesting. So those are my disjointed but thoughts that I had written down.
Great. Well, that's great. Perfect. Dovetailing off of that a little bit, we talked a little bit about the simulator tool, but what emerging or state-of-the-art monitoring and minimization techniques for entanglement could be considered for offshore wind development on the Atlantic and Pacific coast, mostly the Pacific, I'd say. So Lauren, do you want to go first this time?
Sure. I think that some of the strategies you've outlined are going to be great resources, getting out there with the ROVs, but also I believe that if there were these secondary, the marine debris that could get caught, or I've heard from fishermen that tell me that their own gear gets tangled up together, and then you get these big things called rosebuds of gear that would just be traveling along. And I would imagine that would cause a lot of stress and tension on some gear. So if there was a monitor for that, that would easily be able to say, hey, there's some gear that's snagging and cutting a lot of drag, or potentially there's a whale that's entangled with the line. So I feel like all of those would be really helpful for staying on top of if there was some issues. A little bit more real time than just an ROV survey every once in a while.
Yes, that totally makes sense. Desiree, do you have anything to add?
Thanks, and thank you, Lauren. I'm excited to be on this presentation with you too, and I look forward to working after the presentation with you. I think, Alicia, you guys have mentioned in the brief, as Lauren just referred to, because the industry is so new, there's a bunch of really smart people who are trying to come up with really great ideas to move this sort of dial forward. The best available at this point, are these sensors, which I think are phenomenal, to detect different load changes, because of course that's important for the environmental aspect, but it's also important for the mechanical and technical aspect of the cables. Having those extra loads is not good for the systems. So that's a great sort of combination of both industry and environmental need. ROVs, I think the other thing that we're really hoping that the simulator will show is, as Lauren was mentioning, it is tempting to sort of say, these cables can be compared to fishing gear, and I think that that's what we're likely to do, just because that's a reference that we have. But quite honestly, these are very different pieces of equipment, right? First of all, the fishing gear is kind of designed to entrap and sort of engage with the animals, whereas as you mentioned, the design behind the mooring systems is really to keep the wind turbines afloat and to reduce strain on the system, reduce the looping and ability for it to actually entrap. But at the same time, there's a huge size difference. Generally with fishing gear, you're talking about 1/8 of inches, and here we're talking about multiple inches in diameter for these cables. So, as far as the monitoring and there's a lot we can learn from the fishing industry of how to move forward, but we do have to keep in mind that we are having a little bit of a different conversation as far as the actual thinking behind the design for these two different systems. So yeah, I really do hope that our simulator is going to lead to more recommendations of where we can perhaps improve the design of the systems. If there's an area that we sort of see in the simulations or the scenarios that comes out and says, oh, hey, if you do this shorter, if you do this bigger, or if you do this more taut, or, those are definitely elements that we would explore moving forward with industry. So watch the space.
Yeah, no, absolutely. And just to follow up on that, because I personally am super interested in your simulator tool. So I have two questions about that. First, do you know a timeline of when that simulator tool will be complete in terms of like the progress of the study? And then also, is that tool going to be made available externally outside of NOAA and BOEM, or is that more an internal tool for your purposes only?
Thanks, Alicia. Those are great questions. So as far as the timeline is concerned, well, to be honest, when you start these research programs, you think, oh, well, you'll start and you'll finish. And of course, we all know that that's never how science works, right? You always have more questions. So the first phase, I would like to say, hopefully, is going to be ending in the middle of next year in 2023. And that's going to be sort of our fundamental simulator. But of course, as we've gone through it, we've realized, oh my gosh, it would be great. Can we add more species? Can we add more scenario development? So hopefully, we'll be able to acquire funding to move the project forward. So it won't end, but the first phase will hopefully be available by the middle of next year. As far as the availability of the simulator tool, at this stage, it's really going to be a tool that is used by managers, right? Like, so NOAA and BOEM will have access to the software. Clearly, we're making the information available to industry and stakeholders for use. But as you know, it's a first phase, and we've sort of got to standardize the actual use of the tool. And so we thought that would be sort of the more sort of standardized way to approach it, is use it as a management decision-making assisting device, as opposed to sort of, I don't want anybody to get the idea that this is going to tell us everything. It is just a tool in the toolbox that we're hoping will move the conversation forward.
Great, excellent, thank you. Okay, I have one more question from me before we move on to audience questions. But this one, Desiree, we'll start with you. And this one is about cumulative effects that we've talked about previously with Rebecca and Jim. But where do you think the most likely cumulative effects will be with other activities? And what are the associated challenges with cumulative impacts analysis? So Desiree, do you want to take a stab at that first? Sure,
thanks, I guess. Yeah, so I'm gonna tout another study that BOEM is recently funded, and I'm going to sort of focus on the West Coast side of things for the moment, if you don't mind. So understanding cumulative impacts, and I'll refer to sort of what Jim and Rebecca mentioned earlier in a minute. You've got to understand where your baseline is, right? As we spoke about with the acoustics earlier this morning. So I think it's really important that we take the first step in understanding the vulnerability of the different marine mammal and sea turtle species, as an example, along the West Coast. And so we're undertaking that kind of study to form the basis of how best to proceed with a risk assessment. And that approach will highlight data needs. It will also provide a relative context for which species are more vulnerable to additional risk based on their current status. Because, we know that not all species status is the same. For example, in the Atlantic, you wouldn't compare a North Atlantic right whale population status with, you know, sort of a growing population of fin whales at this point. So it's really important to understand, you know, the behavior of the animals, where they occur, what the current challenges are facing the animals. These are all important elements to add to that conversation, to understand what their vulnerabilities are. And from the vulnerabilities, then we sort of move on to understanding and identify, you know, the cumulative effects with other activities in offshore wind development. So that is something that we're starting on the West Coast. In fact, and it should hopefully be finished in 18 months. As far as the challenges with cumulative effects analyses go, well, Jim and Rebecca did mention it earlier, and there are many, right? This is a wicked problem that many smart people are trying to challenge and, you know, and rise to the challenge actually. But just to give folks an idea, Jim, I think, mentioned it a little in that as far as the species are concerned, there's different responses to stresses per species. And then you've got individually differing responses within a species. And, you know, as I'm sure you would all agree, it's kind of impossible to collect data on every animal. And so it's very difficult to account for this variation accurately in any modeling exercises. So that's just really a fundamental challenge that people are struggling with as far as modeling is concerned. But then when you're thinking about a single stressor, the problem is compounded when you try to add multiple stresses. So what I mentioned is, you know, you've got a species that's responding to an individual stressor. You've got individuals responding to an individual stressor. And then you've got multiple stresses acting upon these animals. And so it's really sort of a compounding challenge. It's really difficult to tease out which effects are being caused by which individual stresses and, you know, and how the different species are responding. So as Jim also mentioned, it's not hopeless. We do know a lot about different groups, and we do take analogies from other species, whether they're, you know, land-based species or, you know, even humans. So it's really sort of, it's an incremental process. And, you know, folks have been trying since the 70s to really get this right. And in 2014, there was a great advance in a framework development called the Population Consequences of Disturbance, which is a framework that we can use to sort of populate and develop models on. But again, collecting and identifying the bits of information you need to populate these models, it's expensive and it's hard to get. So, you know, I guess my sort of tout for cumulative effects is we're doing the best we can with what we've got, and we're still reaching to get more.
Great, thank you. Lauren, do you have anything you'd like to add?
Yeah, you did a wonderful job of explaining the species level impacts. My brain, having worked with fisheries for so long, thinks about the cumulative impacts of adding more spatial overlap with where the fishing occurs, because on the West Coast, our shelf is very narrow. And so not only do we have the whale species kind of compacted potentially, you know, depending on where the species are that the whales are feeding on, but now we have the fishing gear that can only be set at a certain depth. And now we're introducing where these offshore wind farms would be in a very similar overlapping area of the ocean. So I just think about those sort of cumulative impacts. So I'll keep my answer short so we can get to more questions.
Okay. Well, that's great. Thank you. And I actually, Lauren, I'm going to stay with you just for a second because there was a question here that maybe you have some insight into, but are there additional opportunities to actually partner with the commercial fishing industry to solve this problem at its source?
Yeah, so one of the kind of the things we were thinking about ahead of time was lost gear removal. So, you know, there's the active fishing gear, and if there is gear that is potentially lost after the season, because it happens, you know, there's storms that and other competing things in the ocean, like boats that could potentially take away some gear. So I know that all three of the states off the West Coast have lost gear recovery programs, and especially some of the Dungeness crab fisheries have even more intense after the season gear cleanup. So that reduces the amount of extra gear in the ocean that's not being actively fished. So I think that's a nice way of partnering to stay ahead of this.
Perfect, thank you. Desiree, do you have anything you want to add there about partnering with commercial fishermen?
I think, yeah, you know, I know that there is interest in the offshore wind development industry, you know, to consider how potentially those industry partners could help with this issue as far as, you know, collecting or, you know, advancing or expanding what Lauren was just talking about, these initiatives to go out there and actually, you know, support initiatives to remove gear. I think, and this is sort of stealing some of my thunder potentially for a research gap, and something I actually want to speak to Lauren and her colleagues about is, you know, just the potential to understand how much gear is out there, you know, and Lauren definitely would know more than I do, but from what the limited information I do have, we don't know that much, right? It's hard. We don't have tracking devices on every piece of gear, you know, and things like that. So it's sort of, we're trying to assess the potential risk of it happening. They're trying to, you know, collect information or just remove gear to prevent it from happening. But there's sort of that third element of, well, how much gear is out there and where does it go? Is there a way to sort of get a better idea of that? And then we could, you know, really have a good discussion about how to partner with various stakeholders and solve the problem at its source.
Great, thank you. This question is for both of you. It has to do with other existing offshore infrastructure. So how can entanglements with existing offshore infrastructure inform considerations for offshore wind? And then in addition, how can best practices and novel research for preventing entanglement in the fishing industry be applied for offshore wind? And Desiree, I know that you and I have actually talked about the best practices at length, especially when it comes to the buoy work. So maybe do you want to talk a little bit about offshore wind infrastructure and best practices?
Sure. Well, it's not as sort of expansive as I'd hoped, because, you know, this is a new thing. But as far as existing offshore infrastructure is concerned, that's a great question. And we have looked at, you know, for example, like oil and gas infrastructure, and we know that there is entanglement. We know that, you know, on coral reefs, and, you know, if there's a place for attachment, it seems like this ghost gear will find it. So, you know, as far as best management practices to sort of prevent it, I think it really falls on looking towards, as we were just talking, how do we prevent it at its source? Is there a way that we can design our infrastructures to potentially, I don't know, deflect or discourage that kind of interaction? Certainly, as far as siting is concerned, and I think Lauren mentioned this a little bit earlier, with the cumulative effects, certainly with the offshore wind siting process, one of the very first parts of these multiple phases that the BOEM process follows is to look for these sort of hotspot overlapping areas or areas of high biological concern, and to really avoidance is the best mitigation, right? So staying away from those areas as much as possible is the best practice. And so, yeah, you know, I mean, we're trying to learn as much as we can, and sort of anticipate what we can with what we know, but it is limited. I have to say, you know, we don't know how these things are going to interact, because again, like I say, we don't even know how much potential there is for interaction. So just tout it again, our simulator is hopefully going to do that, and the second phase is probably going to have way more focus on the secondary entanglement element.
Gotcha, thank you. Lauren, do you have anything you'd like to add?
Yeah, I think I would just tie in that we've been working with the Dungeness crab fishery specifically to come up with best management of fishing practices.
Mhm.
And I know that it's probably not exactly the same as applied to offshore wind, but one of the main things they suggest is keeping the line under tension, so having the appropriate amount of scope. And so I would think that would be applicable and has already been flagged. So and just being able to just keep that line under tension. I believe that would probably be the best to carry that across from the fishing industry.
Great, thank you. And Lauren, I do have one more question here for you specifically, I believe. Is there a baseline consensus of whales by species and by population to measure the long-term impacts of wind farms after they're constructed? And is there a website where you can find a consensus if it exists?
Yeah, there's always monitoring that's going on of our whale species populations, and I can get that a good link for you guys to have a reference. And we actually have a website that I can share too, where it's we're keeping track of whale entanglement indicators off the U.S. West Coast that looks at entanglements, where the krill species is, what's going on. So it's kind of a relatively new and updated integrated ecosystem assessment. Let me see if I can copy that and put that in the text too.
That'd be great, thank you. And I have to say your background is very festive.
It wasn't fully intentional, but I'm going with it today. I'm
I
really
love
happy.
it. All right. Well, with that, we just have a couple more minutes. So I'd like to take this opportunity to thank our panelists. Chris, actually, can you go to the next slide, please? Sorry. Thank you. So I'd like to take the opportunity to thank our panelists, Lauren and Desiree, for participating in our webinar today and sharing all of your insights and expertise with us. I'd like to thank the audience as well for joining us as we continue our knowledge sharing in pursuit of our goal of 30 gigawatts of offshore wind by 2030. And the whole SEER team would like to thank Jocelyn Brown-Saracino, Naomi Lewandowski, and Joy Page from the Department of Energy Wind Energy Technologies Office for their contributions, as well as developing and informing the SEER program. And for your awareness, on the slide you can see here, we have 3 upcoming SEER webinars, the first of which is just a few weeks away on December 15th, where we will discuss benthic disturbance from foundations, anchors, and cables, and also the introduction of new offshore wind farm structures and the effects on fish ecology. You can use your phone and scan the QR code and register right now if you'd like. We'll also be hosting 2 webinars in the new year, one of which will discuss vessel collision and electromagnetic fields and the effects on marine life, and the other will be dedicated to bat and bird interactions with offshore wind energy development, both of which have dates that will be announced in the future. But we encourage you to sign up for the Tethys Blast. If you go to tethys.pnl.gov, you can sign up for the Tethys Blast, and you'll get a bi-weekly newsletter on all things environmental effects of marine energy and wind energy, and we will include the announcement for the upcoming webinars there. And so again, I want to thank you all for your time today. Please feel free to reach out to anyone on the SEER team, to the panelists, to Joy also from WIDO if you have any questions, and we hope you have a wonderful holiday season. So thank you.
Thank you, everyone.
Thanks, Desiree. Thanks, Lauren.